If I can divulge a not classified story about the Blackbird 2 and specifically titanium, is that, do you know where we got the titanium from to do that?
I heard
Through
about
shell
that.
companies and lying to the Russians.
Wait, really? Welcome to It's a Material World, the show that uncovers why material science will change the world. With your hosts,
Praneeth Upadhyay
and Tom Miller. In today's episode, the promise and peril of titanium. Hello everyone. In this episode, we're going to be discussing titanium and its alloys. But before we get into that topic, I think there are a few definitions we need to get out of the way. So first, what is an alloy? An alloy is a material that combines two or more metallic elements, typically resulting in a greater strength or corrosion resistance. The next term that will be appearing in this episode a fair bit is microstructure. So what is microstructure? It is a term used to define the appearance of a material on a nanometer to centimeter scale. A material's microstructure influences its physical properties such as strength, toughness, and ductility, which in turn governs the applications the material can be used for. Next, metastable, particularly as it pertains to, well, materials, of course. A metastable material appears to be stable, but is actually capable of attaining a more stable state of existence, given more precise supporting conditions to reach that state of the least and most stable energy. The easiest way to think about this is like a bowling pin. If you hit it slightly, it will wobble for a moment and then return to its upright, metastable position. If you hit it with more force, it will tip over completely, where it is properly in its state of least energy. And materials do the same thing. And finally, biocompatibility. All that means is that a material can function within a living system, like a human body, without being toxic or causing harmful reactions to its surroundings. So those were the four terms that will be talked about a lot in this episode: alloy, microstructure, metastable, and biocompatibility. But without further ado, let's get right into the show. So Dan, tell us about where you work and what you do at your work and why your work is important to you.
My name's Dan Frydryk. I work for GE Additive in Cincinnati. My specific ask when I report to work every day is to help customers, and that can be any number of industries from automotive to aerospace to medical, adopt additive manufacturing. My specific expertise is in titanium, and that's across two different modalities inside of the additive space. I am the go-to person for electron beam manufactured titanium as well as laser. And because electron beam is a little bit niche, I'm also asked to do a lot with the other materials inside of that platform. And so has a lot to do with Ti-64, which is the workhorse of the titanium alloy family, as well as some of the commercially pure titanium alloys. And I shouldn't even call them alloys because they're pure. So already misspeaking. But the other alloys inside of the titanium family. At the end of the day, that's what I attempt to do is work with my mechanical colleagues and our collective customers to work them through the material selection as well as development. And that extends all the way to characterization of properties through various temperatures, or in the case of fatigue, different stress ratios, as well as the qualification of machines and setting limits and specification values all around titanium specifically. But like I said, with the electron beam side, could be a number of other materials as well.
A quick follow-up to that. So you said your primary MO here is to be the EBM titanium alloy specialist, but particularly Ti-64, which is this workhorse alloy. Speak to that a little bit. Is there enough demand or enough of an interest in this we're just talking one alloy system. Is there enough demand present for there needing to be that sort of speciality within a company? And why is that the case?
There's far more to know about a single alloy system than you could possibly imagine going in. So a lot of times will be approached, whether it's by colleagues in additive or friends that know I have a background in metallurgy, and they'll say, "Hey, do you know about this other random alloy?" I'm like, no, because it's frankly there's just too much out there to know, and adding copper to one alloy system, adding copper to another alloy system makes one super strong and the other one, susceptible to crevice corrosion. To shortly answer your question, Tom, the answer is yeah, absolutely. There's the need to have speciality in specific alloy fields because if you know a little bit about something, that's enough to give somebody the wrong answer. If you know a lot about that thing in that specific system, you can really start to dive deep and understand the requirements of your customers. So the more you know, the more dangerous in a good way you could possibly be when it comes to applying that. So specifically with titanium, it's something that your average, everyday consumer, a normal person is probably not going to run across. Unless ride an expensive bike or have expensive golf or tennis equipment, right? It's just not something that you see a lot of. So it's kind of a novel material when it comes to what individuals know about it.
So since classes don't necessarily focus on titanium, I was wondering, how did you get so immersed in this world, and how did you get so well versed about this topic?
So right off the bat, I won't say I'm a titanium expert, but it is what I deal with every day. So I think I'm okay to talk about some of these things. But I got introduced to titanium as an alloy system when I got my first job out of grad school. And what I was doing was working for a forge shop. So we're making critical rotating parts for the aviation and energy sectors. So anybody who makes a turbine, so that would be GE, Rolls-Royce, Snecma, Safran on the aviation side. So any of these discs, blisks, shafts that spin, and as soon as you start to impart that kinetic energy, these things get dangerous. So we therefore call them critical, and we pat ourselves on the back because we had to keep good records and buy nice material to make all that stuff happen. So actually, when I started, the customer that I was the process metallurgist for was focused mainly on titanium. So I got started by doing the 6.4s of the world in terms of aviation quality parts. Really, when you start to take a look at the differences and the things that I learned about in school that were not applicable anymore, you say, well, hang on a second, why the heck is this alloy so much different than the other one? And it just kind of makes you have an appreciation for the level of knowledge that needs to go into each and every individual alloy system out there. And as I started to dive more and more into titanium, I just had a respect for its relatively recent history. So 1950s, I think, titanium starts to come onto the field. So that alloy as an engineering material is as old as my parents, which is weird to think about. It's not been around that long. It's just cool to think about. The other aspect of it is uniqueness or the novelness of it. I'll tell you a sidebar story real quick, but one of the things that I did as an alum of Virginia Tech, at Hokies, I participate in this diversity program where we go back and we help kind of guide an engineering design project as GE through this camp called CTech Squared, which is a 2-week residential program for rising junior and senior high school women who we want to get into STEM careers and then become Hokies too, which is, I think STEM is priority 1, Hokies priority 2, and then as GE, priority maybe 2A is to come work for us as value add members of our company. But one of the things that I do when I go there is just as a thank you for high level participation, I give them this lattice looking Virginia Tech logo and hand them out. I pick them in their hands and I'm like, this is titanium. It's like, yeah, it's titanium. It's normal to me, you kind of get jaded to the fact that it's possibly something that they've never touched before and put on this high pedestal. And on my day-to-day life, and when I was at the Ford shop, it was secondhand to be like, this is titanium. It is the titan of materials, it's got a name that reflects what I believe it's capable of. I do get to sit back every day and think about the fact that I'm working with a new alloy that is unfamiliar to a lot of people and one that is capable of pulling off tasks that many other systems are not. As somebody who gets to work with these crazy materials, these novel materials on a day-to-day basis, it is hard to remember that, this is unique. There's not a lot of people out there doing this.
That's really cool because Tom, after his internship, showed me his titanium business card and everything. And, I had never interacted with titanium, especially in a business card format. So I thought it was just super cool.
I would say probably that I'm responsible for, at least there's less than 15 sets of those rolling around. So Tom can be among a club of people that could only be counted on fingers and toes.
I've always been looking forward to be part of the Fingers and Toes Club at some point in my life, so I'm honored that this is the way it happened. So I will say, to put it lightly, you've spoken quite highly of titanium and its alloys, which is fine. You're in good company here to do that sort of thing. But I want to dig into that a little bit. So what makes titanium a useful alloy as compared to this broad scheme of lightweight alloys, such as aluminum-based alloys that are also out there on the market? And how are these advantages born into the microstructure of titanium and its alloys? And maybe there's something of an emphasis on Ti-64 here because it is that sort of workhorse alloy.
So to be fair, the application of titanium and specific engineering use is niche. There are a handful of places where you can use titanium and nothing else, and many, many more where you can opt to use something that's maybe cheaper or more readily available. But then you start to sacrifice things like section thickness, for instance. You might need to use more of a material or use other fasteners or more fasteners, or applications where you'd have to perhaps limit the temperature that it's capable of. So let's actually start with aluminum and compare it to some of the steels out there, right? You think that those are two hugely different classes of materials, but when you start to look at things in an air quotes specific sense, so if you're talking about specific strengths or you're comparing a strength to weight ratio, you start to actually find that some of the steels and the aluminums are, on the same playing field. So where if you could have like a 3-inch thick bar carrying load of aluminum, you could use, I'm just going to make up a number, but 3/4 of an inch thick bar of steel doing the same thing. So titanium plays in that same world too, perhaps between those two in most instances. But you start to get into a world where aluminum will start to lose its strength at higher temperatures. And then perhaps you're starting to temper out some of the properties in steel that titanium doesn't have that problem with. You just start to raise its temperature. When you just start to look at the light alloys, you put titanium, aluminum kind of in the same conversation because of the light materials. Those are probably the ones that are out there the most. And then you look at maybe magnesium as an engineering alloy too, but now we're getting, I think, even more rare than titanium these days for a number of reasons. And I think the other half of your question was microstructures. To get really into the weeds, the titanium families are classified typically as alpha, alpha beta, or beta materials. Inside of those, there's other things like near alpha or super alpha, all that stuff, but we skip that for the sake of today. So the alpha and beta are the broad phases that you would see in a titanium alloy. And so the Ti-64, for instance, is an alpha beta material. So the 6 and the 4 in Ti-64 are aluminum and vanadium, and those individually are alpha stabilizers and beta stabilizers. So that's how you get both of those to exist at room temperature. Commercially pure titanium, where you have nothing but a couple of atoms of probably oxygen in there, is alpha at room temperature. And then so you can imagine to retain beta, which is kind of metastable at room temp, you have to add in a substantial amount of stabilizers of that. So you'll see things like the alpha materials, which because they're the same phase at high temperature as they are at low temperature, you cannot heat treat. You can't really get away with strengthening it. So you have to use it kind of in its natural state. So inside of the GE Additive space, we have an alloy called Ti-6242, but those are there to essentially stabilize your alpha and also have some other strengthening elements in there. You also want to be able to strengthen it somehow, and that would be where your extra alloying elements come in. But like your alpha alloys, because again, they don't go through a phase transformation from room temp to higher temp, you can expect those to be used in high temp applications and things that are perhaps sensitive to creep. So that's how you might tailor one of the phases inside of to a specific choice. So alpha, stable from top to bottom temperature range, that kind of gives you confidence that you could use it at a high temp. Other half of that would be something like a beta alloy. So we'll talk alpha beta in a minute. Your beta alloys contain so much beta stabilizer that they aren't actually, could be considered metastable at room temp. So much so that there's a couple of alloys out there that if you even slightly look at it funny, it'll recrystallize and actually go through a phase transformation. I joke about that, but there's some things that if you impart a few percent of cold work onto something, that's just enough energy to get it to kick over and actually move from a beta alloy back into an alpha beta alloy. Beta is only metastable at room temp. If you add some heat to it, you can't possibly use it at high temp. So that's your two opposite ends of the same spectrum of where you can think about how microstructure plays into properties is you have alpha, which is the microstructure that in phase constituent that pure titanium wants to be at room temperature. And then you have beta, which doesn't want to exist at room temperature at all. So you can kind of pick and choose your applications based on what the alloy is used for, what you might want to, the applications you pick an alloy for based on what its phase amount is in those particular areas. The sweet spot that the industry has settled on is this Ti-6-4, which is an alpha beta mix. And like I said, it's aluminum and vanadium, and they're alpha and beta stabilizers. So both are relatively happy to exist at room temp. That being said, as you cool your Ti-6-4 from its elevated temperature, so you're going to forge it, right? You can either forge above or below what they call the beta transis, and that's at the point that beta starts to exist as 100% on your phase diagram. So depending on what you want to do, you can tailor the microstructure of your material based on processing, and that's forging or heat treating barely above or barely below your beta transis. So 6-4, it's the workhorse because it's still machinable. You can use it at cool temperatures. You can use it slightly elevated temperatures. It's famous for a reason, and it's because it's broadly applicable to a whole number of applications in the engineering space.
So based on the microstructure and the properties, I wanted to delve more into how titanium can be used in the aerospace field. We did our research. We saw that the SR-71 Blackbird is, considered the fastest aircraft in the world for 30 years. And it was primarily made of titanium alloys, I believe. And so I wanted to hear your thoughts on why they chose titanium as opposed to any other metal alloy.
We get back to another temperature application. So the name of the game in aviation is specific fuel consumption. So how far can you go? What's your bang for your buck when it comes to what a gallon of fuel will get you? When you're flying Mach 3.5, I think, maybe it doesn't get you that much anyway, besides, reconnaissance and 2 armed forces members that come home at the end of the day. I think that's the evasive maneuvers strategy for the SR-71 was just hit the throttle, right? Just leave, just keep going, and you've outrun everything else. So that's crucially important. But as you're just massively burning fuel, you also want to be as efficient about that as possible in a certain sense. Now, the speeds that this airplane was going, 3 times the speed of sound or more, are just going to hugely heat up the skin of that aircraft. And I don't think that the skin of that was titanium. I think we're talking structures and things on the inside of the aircraft. But all of that heat needs to go somewhere. And a lot of time it's going to make its way into the superstructure of the aircraft, whether it be wing spars or fasteners. You have to be able to deal with the heat in your structure and not weaken the actual material itself. So titanium is a natural choice for, again, that low density material, but also be able to retain the strength at temperatures that speed was causing the skin and therefore the rest of the structure to heat up at. Do you know about the fuel tanks?
Yeah, I heard about the fuel tanks thing,
Yeah.
that they waited for thermal expansion to actually keep the fuel inside.
Yes, if you filled the fuel tanks up and just at room temperature on the runway, they would just leak because the aircraft, it got so hot, you needed to do something with the coefficients of thermal expansion and stuff running into each other. So it was just decided that the fuel tanks were going to leak at room temp so that they would be solid or leak free at the elevated temp that the airplane was actually, operating at. But so much so that they put just barely enough fuel in the aircraft for it to take off. And then they would refuel with an airborne tanker. And then they would refill once the plane had heat up a little bit, and they could actually change the fuel. That airplane's an engineering marvel, and I think anybody from Lockheed would agree with that. There's also tons of room for improvement, I think. The airplane was so fast and so new that they needed to be able to deal with the heat and pick an engineering alloy that was going to be up to the task. And some of the earliest choices for titanium were, capable of such things. But if I can divulge a not classified story about the Blackbird 2 and specifically titanium, is that, do you know where we got the titanium from to do that?
I heard
Through
about
shell
that.
companies and lying to the Russians.
Wait, really?
Yeah. So a lot of the titanium is manufactured comes from this mineral called rutile, which is just essentially dirty titanium dioxide. To process that, it has to be made into sponge and some other things. But Russia early on is one of the places that was either doing this the best or the earliest. So in order to actually source titanium into the US without it being obvious that it was a military application, the CIA bought a lot of, I guess they incorporated a bunch of shell companies. So they just played like hide the actual owner with a number of countries, the one obviously of interest being Russia. So we brought in a lot of the royal we, because I was not alive in the 60s, nor working for the CIA, I will point out. But we brought in a lot of this material. And frankly, I don't know, and the sources that I can find are mostly unclear in looking at this story because it interests me. A lot of either raw material or titanium through shell companies because they didn't want to know that it was going to be a military application buying in huge amounts of the stuff. But when you think like it was some of the first titanium brought into this country was probably used in large quantities for that project. You also have to realize there was no real method to weld the stuff yet or machine it or not knowing what coolants you could use. Lockheed learned a ton of stuff about titanium in just the first couple of months or years working on SR-71 and its predecessors. So I think a lot of what we know about how to deal with titanium was developed by Lockheed in that era, just because they had to learn because it was the only capable material for that lightweight and high temperature application they were interested in.
To speak to one more issue in the aerospace industry that came up with respect to titanium is so obviously the SR-71 Blackbird is a great example of a success. I mean, obviously the plane was kind of eclectic, for lack of better words, but obviously it did its job quite well. But another application in the aerospace industry where titanium didn't prove to work so well was in the Sioux City incident, which happened so many years ago at this point. So speak to the incident that occurred there and how that played into a situation where titanium's properties bit instead of fortuitous for such great applications. So a little bit of context into the Sioux City incident. In 1989, the United Airlines Flight 232 crashed in Sioux City, Iowa, killing 184 of the 296 people on board. There was an explosion in the back of the airplane, which was caused by a fan disc failure in the tail engine. This fan disc had a half-inch crack that was entirely missed by human inspection. The creation of the fan disc involved melting titanium, which is a complex process to say the least. If it's exposed to oxygen in high enough quantities, it forms a phase called hard alpha, which is very brittle and weak compared to the surrounding alloy material. Due to the formation of this weak hard alpha, a significant crack had formed, eventually leading to the catastrophic failure which caused this incident. So now, on to Dan's response.
I'll tell you, like, because of my first job being somebody who essentially would have made that disc that blew apart, that was, I don't know if I want to say my first day, but for sure the first week, I forget it was our quality manager or the head of engineering, whatever, came downstairs and he points us to the URL. I want to say he slapped a book of like the Sioux City report on the table, but he didn't. He was just go read the actual report. It's a hugely lengthy report about how it happened and the failure analysis that they did based on that. But so clearly the root of it, right, there was a disc. It was uncontained failure, as they'd say in the aviation industry, got thrown. What they come to find out is that there's various elemental and microstructural features in there that are detrimental to the behavior of your actual part. So the Sioux City thing was what they'd call a hard alpha inclusion. And the finding of the little booger inside the disc that got broken and ejected was that essentially the melt practice for some of the titanium materials was not yet well understood and well characterized. So if you go to an engine manufacturer or somebody who's using titanium in a truly critical application, they'll tell you that you want to use a titanium that's been melted and remelted a number of times. And what that does is that helps to eliminate some of the inclusions that you actually might get in some of your materials. So if you were to go kind of Googling around for providers of quote unquote, there's actually a technical term, premium quality titanium, they would tell you how they actually manufacture it and all of the history of how much scrap was in it, what the chemistry was. And then you do things like take a slice off of both ends of that ingot, and then you can do something called macro etch it, which is, metallurgically you'd etch the plate, but it reveals things that you can see with your eyes rather than like a metallographic microscope. And so they're looking for things like those inclusions where the presence is going to be detrimental to the behavior of your part. And certainly, and perhaps maybe none more famous than the Sioux City incident was the finding of an inclusion inside of that. The aviation industry has found their way around by using a manufacturing method for their raw material that involves screening of the input material to a very specific level, and then the melting procedures are chosen. But the aviation industry has thought about what happened and continues to think about what happened every time there's a failure. They address every single portion of that kind of supply chain and say, where could this have been caught? Where could this have been better? And specifically with Sioux City, there were a number of findings, but none stands out more to me than the introduction and the nailing down of what premium quality titanium looks like. There are titanium plants out there that are so worried about tungsten inclusions that they'll make you leave your ballpoint pen outside, and they will give you a tungsten-free ballpoint pen to take inside the facility. The ball of your most thick ballpoint pens, for instance, is tungsten carbide. And so if that finds its way into a furnace somehow, and I really don't know how that would happen, but the tungsten inside of your tungsten carbide containing ballpoint pen concerns the aviation industry and titanium industry as well, to the point where they'll give you a tungsten carbide free ballpoint pen when you walk in the door.
So to shift gears a little bit, so outside of the aerospace space and into more the realm of things on the ground. So once again, also going back into Ti-6-4, why is Ti-6-4 in particular such a popular material for applications within the human body? And what are these material properties that it has that makes it so biocompatible?
I'll do a little bit of correcting too, is that commercially pure Ti has a home in the body as well. So 6-4 is a higher strength by substantial margin, almost 2x over the pure titanium. And the Ti-6-4 and CP Ti, so commercially pure titanium or CP Ti, share the same reason to be biocompatible. And a lot of it has to do with the oxide layer that's formed on the outside of the part. And so that's the same reason that titanium can be used in chemical plants too, is that unlike an iron or something that forms its oxide and then promptly sheds it, right? Rust is a terrible oxide. Titanium holds on to its oxide viciously. So TiO2 is a very, very stable compound. It's adhered really, really well to the surface, to the point where that's what makes you biocompatible and chemically compatible, is that you're actually butting up against what amounts to a ceramic, right? It's TiO2, as opposed to a metal material. So the chemistry of TiO2 versus a huge number of acids is really, really safe, never mind what amounts to a relatively benign environment inside of your body. So when you think about etching titanium, the etchant for titanium, if you were to do it in a lab, contains hydrofluoric acid, nitric acid, and I think just distilled water was something to fill the gap, right? So a substantial amount of that etchant is hydrofluoric acid, probably going to stand up to maybe non-stomach parts of your body okay. If we're relying ever so slightly to eat away the surface of titanium with hydrofluoric acid, the statement remains that you can use it in your body with relatively, little risk. Part of the other bit is that when you look at the alloying elements in titanium, so the aluminum and the vanadium, aluminum's not like one that you want floating around a lot, but when you look at the prior history of what we used to put into our body. So a couple of the first implants were, 316 stainless or cobalt chrome moly. You start to get some things that have nickel inside of them, and a lot of people have allergic reactions to nickel. So the composition of Ti-6-4 is actually amenable in its own right, for the most part, to be biocompatible. And then you have the addition of that oxide layer on the surface that prevents further attack by the juices, essentially, that are flowing through your body at any given time. Now, that being said, titanium is not great in applications where, it rubs on itself. It likes to give off particles. So when you see things like hip cups or knee implants or some applications like that, you'll never see a metal on metal joint. And besides the fact that it just sounds painful, one of the things that you definitely want to avoid is having titanium rub on itself or another hard material, because it's quite poor in wear applications. So you will see titanium a lot in static situations. So things like cranial implants or implants that are going into your spine where they're going to fuse bone around that anyway. Or, like the hip cup where it's put into the acetabular cup part of your pelvis and then the bone grows into it. It's not going anywhere either. So you'll see a lot of applications where the motive or the motion half of the hip application is not titanium, or your knee, for instance, because of the fact that it's a bad in wear application. So you either need to be cognizant of what's touching what, or put like a load-bearing polymer in there to kind of lubricate the joint, as cartilage might have once back in the day.
So you mentioned, hip cups is one of the current applications with titanium. What other applications are involved with titanium and the human body right now? And also, what do you envision Ti-6-4, other titanium alloys used in the human body in the future?
In terms of what we're presently using for, and I can talk specifically about some of GE Additive's customers, are things like spinal implants, cranial implants. To go on a tangent, and I'll get back to your question, Puneet, about where we're using it, is part of the beauty about additive, period, titanium or not, is that you could make a patient-specific implant. So let's just say you go in for an MRI or a CT scan or something because, not to be gruesome, but you got in a bad car accident and part of your skull is missing, or needs to bits and pieces or something like that. And so instead of, typically what would be done is you'd go get this one-size-fits-most piece of sheet titanium off the shelf, and then your surgeon would do something to make it fit you and then screw it into what's left, right? So instead, if you have the couple of days to spare, you take your digital data, which amounts to your CT scan or MRI, and you can make an implant that literally fits you and only you for your injury and only your injury. So again, regardless of the fact that it's titanium or not, you can print perhaps in the the surgical center of additive excellence at some hospital someplace, and that could be depowdered and put into you within 18 hours, 24 to a couple of days. You could see this world where additive fits this patient-specific model really, really nicely, because it's just a file, right? You don't need to make new tooling for it. It doesn't need to go through a complicated manufacturing cycle. Have an engineer and doctors that can input this data essentially and put it through some post-processing, and you get your part out, and then that's made available for implanting into you as a person, and again, only you as a person. So it is a cool application of a micro factory is every additive machine. To continue down the titanium route, I don't know that there's anything that we haven't, as a humanity, right, thought about replacing with titanium that we haven't already. So there's portions of rib cages, portions of heads, spines, knee, hip implants, but all the plates and screws and stuff, if you ever have a bad break or something like that, can be titanium, sometimes stainless as well. I'd say everything that we probably want to do with titanium has been tried, whether it's been done regularly or with any degree of frequency. I can't say exactly, but we will continue to push the limits of healing people with whichever means necessary, and the biocompatibility of titanium is a huge fit for that.
That's really cool, because I actually read an article, and it was from the Oregon Health and Science University. They basically designed a durable artificial heart that uses titanium for the two ventricles. And the way it works is one titanium tube actually contains a hollow rod that's coated in a titanium alloy. I'm not sure which one. And that shuffles back and forth between the tube. And so kind of that.
So it's just a mechanical valve that's using a solid material. So when we were talking about the oxide layer on titanium, it's good at what it does. There are other layers you can put onto titanium. So a very famous one is titanium nitride. So if you've ever walked into Lowe's or Home Depot and you see these drill bits on the shelf and they say, these are made of titanium, and you're like, probably not. What they are is they have a titanium nitride coating on them, and it's crazy, crazy hard material. It's super scratch resistant. It's going to, win the day against wood and aluminum and steel every day, as us, Joe Schmoes are kind of doing stuff around our house to repair some things. So perhaps the thing that it might have been coated in was titanium nitride if it's a wear application. So that my statement from before, which is titanium uncoated is quite poor in wear, is turned on its head. It's actually the opposite if you nitride titanium, because it becomes really, really hard and is actually phenomenal in wear applications. So if you do have something sliding like that, and a coating like a titanium nitride would be super beneficial. So not only can you nitride a base of titanium, so if your bulk part was titanium, you could nitride that, but you can also deposit titanium nitride on other materials and actually give it the coating. So you can have what amounts to a composite material of, let's just say, an alloy steel coated in titanium nitride that has the benefits of the cheapness of alloy steel and perhaps the toughness of the core. And then you get to your outside and you get a super hard layer on it that's doing cool things with its environment.
We talked about aerospace and we talked about healthcare, and our podcast is designed to talk about how material science appears in our everyday lives as well. So
Yeah.
I wanted to hear what you thought about, where could an average American expect to encounter titanium and its alloys in, our everyday life?
I think I have a bad answer for you, unfortunately, which is either probably not or you got to be rich. It's so for sure, like the stuff that you have in your house has touched titanium in its past. So a lot of, let's just say, cleaning chemicals underneath your sink have been processed in plants that have titanium tubing of some sort, or perhaps the solid gold of toilet paper these days had some titanium in its pulp and paper processing facility because it does good things in those types of caustic and corrosive environments. So when you look at your toilet paper, you might not be touching titanium, but that probably did touch titanium at some point in its life. So as consumer goods, the actual amounts of titanium you see are going to be relatively few and far between. But the stuff you might take for granted that was processed in a plant that contains titanium is everywhere, probably in piping applications or, impellers, things like that, that could be in a nasty bath that's being used to, either oxidize or reduce something into a material that it once was not. So, but if you want to talk about stuff that somebody has in their house today, one of the obvious things is jewelry, right? So you've probably tried on or know somebody that has a watch that's got a titanium band on it. So it probably looks a lot like stainless steel from far away, but when you pick it up, you do that thing where you're expecting something to weigh 30 pounds and it only weighs 2. Titanium is finding its way into wedding bands and things like that as you're looking for something unique to say, like, oh yeah, my wedding ring's titanium for whatever reason. But like I said, the drill bits are coated in titanium nitride. You could see things like bike frames or tennis rackets, or there's a couple of places you could see it, but everything that I just listed was something that you're probably going to need to have paid for and you'd know about. You're not going to accidentally stumble into your kitchen and realize your measuring spoons are made of titanium. There's other materials to use that are just more obvious than titanium to use for most things around people's houses. It does exist in a world where there's a reason for you to have opted for that premium, and that it needs to have been a conscious choice, or you probably will know something about it when you had made that decision. You mentioned biomedical stuff a while ago, and as we as a medical community are increasing people's lives and livelihood, you're going to see more and more people that are bionic, right? And I say that, with a little bit of a wink here, because your dental implants or a new hip cup or getting plates and stuff that are, related to bad bone breaks and things like that, you will probably know somebody in your life who's got titanium implanted in them. And so in fact, my mother's got a couple of pieces in titanium, and I always ask her to ask her surgeon if he can send me the material cert. And that's kind of a joke, but what it's made out of and kind of where, the manufacturer of that medical device is. So I would wager between the three of us, one of us is going to have something titanium in us before the time we all move on to greener pastures here. Yeah. I think it's Tom.
Yes. I mean, it's good for me, right? I get titanium.
So, Puneet, to answer your question, in general, people aren't just going to stumble on titanium. They will either be pointed out to them, they will have paid a premium for it, or their doctor is going to give them no other choice.
Which is to say, though, that even though a average person may not work with titanium or experience titanium in their day-to-day lives, which is to say, though, that our lives are enabled by being able to use titanium in a number of manufacturing applications.
Yeah, exactly. And so, I mean, if you were talking to somebody who worked at, ExxonMobil or one of the companies that processes chemicals all day, every day, they're going to take for granted the fact that commercially pure piping exists. You could, for instance, you go on McMaster Car right now and buy a piece of titanium. It's out there. You can buy it as a person. You could make a doorstop out of it or a business card out of it. But the question is, why are you doing this? Because at the end of the day, a lot of the thing that rules the day is somebody's pocketbook or wallet. Yeah, and so there's no reason to go after it if there's something else out there that does a much, much better job cost-wise with perhaps no discernible detriment for having chosen something else.
So aside from what we deal with every day, we've started to touch on a number of future applications, but totally industry agnostic, what do you see as being a potential future application for titanium and its alloys that you see to be potentially promising?
titanium in its own right, I'm not going to say it's played out, but of the community that cares about titanium, there's not been huge strides made in the metallic version of titanium in a while. So we're finding new things to do with it, pushing the boundaries, finding coatings that you could make out of it or put on it to do some unique and novel things. So when you start to think about perhaps the exotic alloys or unfamiliar ones, you start to think about things like the titanium aluminides. So titanium aluminide being an intermetallic material that contains titanium, aluminum, and niobium. They're starting to make turbine blades out of that for the aviation industry. So you get the benefit of having lower density aluminum alloyed with your titanium. So we're already talking about light alloys and how titanium's pretty good at that. So now you add a less dense material into that. And by the way, you're getting an intermetallic out of it, which actually withstands higher temperatures. So you've gone and blown away my prior statement to say that titanium is one of the best for high strength to weight ratios, but can also handle temperatures. Because now I'm telling you, go put this aluminum in there and it gets even better, right? It certainly doesn't come without its detractors or detriments, which is it is an intermetallic. It is enormously brittle at room temperature. There's papers out there that their findings are less than 1% ductility at room temperature. So if you just look at it funny, it's just going to shatter. But if you're going to put it in the hot section of an aircraft engine where all you really need to worry about it is the couple of cycles it takes, hot gases flowing by before it starts to gain some of its toughness. Yeah, it's got good applications in those situations. But again, I think titanium aluminide is even worse than Ti-64 with how often you're going to see it. I will never, ever in my entire life find a use for it in my house. I don't think. I can't, honestly, because my house is all room temp. I don't know what's going on if I'm at the applicably useful temperatures for titanium aluminide. I think that specifically the intermetallics of titanium are probably going to have their day probably in the somewhat near future as we're starting to recognize that we've kind of come up against what we might be able to do with the known materials inside of titanium. And now we're starting to use these ones that are hard to work with. So all of the titaniums to date are chosen because they have a use, but you can also manufacture them. Titanium aluminide is processable through electron beam melting, but you can also, and in the additive space, but you can also cast it. But the yields, so like first time yield of these parts are enormously different depending on the method with which you manufacture it. So in a casting, right, you're going to have odd cooling rates depending on section thickness. And with intermetallics, such a difference in thermal gradient is enough to crack the part and then cause it to be scrapped. Because of the hot chamber temp of EBM, you can actually start to think about tailored cooling rates and make sure that doesn't come down from temperature too quickly. So then you have much, much higher yield in the additive space in EBM. So you couldn't even process titanium aluminide in laser because of the speed with which a laser part would cool off. You really get the benefit of titanium aluminide in EBM because of the vacuum environment and how slowly the powder bed cools off once you actually start to begin processing parts.
So to speak to the future a little bit more, and obviously additive has come up a few times in this conversation for some reason. I don't know why. However, to speak a little bit to the future of titanium, why is titanium such this popular material in this additive manufacturing space?
The reason that they have applications in titanium first and foremost was because of the industries that required it. So when you start to look at what we've talked about already, you have aerospace, medical, and some of like the high-end automotive or consumer goods applications are the ones that can afford this relatively expensive manufacturing technology as it's new. And so those people had the applications that were then titanium. So then titanium got brought into the fold. And so as a little bit of kind of background as to where RCAM, so the electron beam GE Additive family comes from, is the fact that they had this brand new novel technique of essentially layer by layer additive manufacturing. And they said, well, who is interested in such a technology? And then that pointed them to the medical field, and then the medical field pointed them to titanium. So there is no intrinsic reason that EBM and titanium play together super nicely. It's a coincidence that they do. It's nice that RCAM has figured out how to do it very well, but it was a development of the technology, find a customer such a thing, what's critical to their quality. And that would be the actual biocompatibility, therefore titanium. So to say that titanium in the additive space plays well is kind of a backwards thought. It's really what industries does additive play in, and then what do those companies want for their applications? I promised you to round out with laser, and EBM and titanium, like I say, play quite nicely together because of the history in RCAM and the titanium using medical field. It's a little bit later to the laser game, not a whole lot, but a little bit. And so we actually experienced some problems with cracking in our titaniums inside of the laser field, again, because of residual stresses that can be built up and some of the heat modeling that goes on. So even to kind of push back a little bit on your statement, Tom, as to why titanium plays so well in additive space, I could tell you that to develop titanium on a laser machine is borders on horrible. Like, it's not a pleasant experience. So our customers say we want it, so we go make it work, but it's not a great material to develop.
So, I don't mean to be a Debbie Downer, but I do want to get both sides of this titanium story. So I wanted to ask you, what are the main downsides to the use of titanium? And also, on top of that, does titanium production have a significant effect on climate change?
So it's a good question, Puneet, that why might you not want to use titanium? And one of them right off the bat is just the cost of the titanium. We talked about that a little bit already, but it is definitely a statement that it's an expensive material. There's a reason it's not more places. So the question is why? Because titanium is not a rare element in the Earth's crust. I don't know what its number is, but it's not outrageous. It's not like finding diamonds or gold in the ground. It's around. You can find it. If you find it in like swaths and patches, so much like strategic reserves and mines and things in countries that we may or may not be friends with. The similar things exist for titanium too, is that it's only certain places around the world, but it's out there. The question is, why is it expensive if it's in the Earth's crust in relative, in air quotes, abundance? And so when you look at how it's actually manufactured, something called the Kroll process, titanium is brought in, like I said, in rutile or a couple of other forms, and then it's broken down with a couple of methods, but typically is a combination of chlorine gas, and then you reduce that with, I think it's magnesium. You have this environment where you have chlorine gas, and then you have, call it tickle. Actually, it's a funny thing. It's TiCl4, so it kind of looks like tickle. So that's where it gets that name from. So when you think about the process that's used, you start to consider, like, is chlorine gas all that friendly? And the answer is no, not on its own, but we have engineering controls around that and you can deal with it. And then additionally, once you form that magnesium chloride salt, you have to essentially end up with pure titanium at the bottom of the reactor. And so how you do that is you react the other two ingredients, which were chlorine and magnesium later, together, and then get titanium out one side and a combination of magnesium and chlorine out the other. Both of those, best I understand the process, can be reused. So it's not like a huge waste. You're not venting the stuff to the atmosphere and never using it again. But it is an energy intensive process because between those steps, there needs to be distillation. It needs to be done at temperature. We mentioned in the Sioux City discussion, premium quality titanium can be melted up to 3 times. So then you're starting to use enormous amounts of electricity to do that. So I haven't seen the actual numbers on recycling of titanium just because it's less common than aluminum. But the reason, like aluminum cans, they have huge reason to recycle those is it's much, much easier to make an aluminum out of an aluminum can than it is to make a can out of raw ingredients of aluminum. So how it was pulled out of the earth, I would imagine the logic follows, right? That if you can skip all of that process of conversion into sponge and things, you're actually better off to recycle it. So its actual environmental footprint, I don't know that I am good enough to know those types of things, but the statement around, is it environmentally friendly material? The answer is probably not, because of the methods it took to get there. And then to recycle it, it would be much easier than to start fresh.
So last topic, I was reading an article about the weirdest things ever 3D printed, and I wanted to hear your professional opinion on this one.
Tom's business card was the weirdest thing I ever 3D printed.
I might have a weirder one for you.
Okay, let's hear it.
Researchers in Australia actually 3D printed lightweight titanium horseshoes for racehorses. But interestingly enough, they chose to make them a stylish hot pink color. So,
okay.
In your professional opinion, I was wondering if you agree with the color choice, and if not, which one would you choose?
You thought this was going to be a throwaway question, but the thing that we didn't talk about with the titanium oxide was anodization. So, here we go, right?
Wow.
So you can
we
actually
got technical here.
Yeah. I told you thought this was a throwaway, but it's not. So the aluminum, you can anodize aluminum, but what you require when you anodize aluminum is a die. So the die kind of fits into these little tiny like vertical passages inside of the aluminum oxide when you anodize it, and that gives you your color. And don't pretend to be a surface finishing expert. I leave room to be corrected on that, but the statement there is true, is that aluminum requires a die to be anodized to a specific color. Titanium does not, and it all has to do with the thickness of that oxide layer. And you're talking about between tens and hundreds of angstroms of thickness of that material. And what you're actually looking at when you see a color is the interference patterns and some of the ways that light plays with that oxide. So I would guess, and I don't know the voltage at which these researchers anodized this titanium to hot pink, but for sure, that's probably how they got there. As to hot pink, I don't know, how colorblind are horses? You think it was trying to distract the race horses behind?
Ooh, maybe. That's clever. That's
I
what
have-
material
I have-
science and
yeah.
engineers are used for.
I have nothing against hot pink. So if the horse or the owner of the horse wanted hot pink horseshoes, more power to him, I guess.
Another quick story there. Actually, I have a very close relationship with the anodization of titanium because we were doing our materials corrosion class and for a big paper at the end of the semester that we had to write, and we got assigned to anodization. And I thought anodization would be super boring. I did not think it would stick with me, but it's actually not. It's really cool. And so what we did for the class is we wrote our paper and we had to give a little PowerPoint presentation because that's the way you end any good college course. And
it's good preparation, Tom, because no big professional meeting is complete without a couple of PowerPoints.
Correct, which I've also learned that. But that aside, we decided to do a demo. One of my good friends had a spoon made of titanium, which they apparently sell. And what we did is we had a bath. It was full of some sort of salt dissolved in solution. I forget which salt, but I presume it was one of the very common ones. We essentially took the titanium spoon, took 2 wires, and I think we connected 2 3-volt batteries in series, and we turned his, right before the very eyes of the whole class, we turned his spoon purple. And we did not think it would work. And we started seeing bubbles, and we may or may not have mildly screamed, and it was fantastic. So all of that aside, so we've had a pretty wide-ranging conversation about titanium and its various applications and its promises and perils. So if our listeners to this episode could take 3 things away about titanium, what would those 3 things be and why those 3 things?
Sure. I think what I was surprised to learn the most was the relative age of the alloy system. So you'd probably be hard pressed to find somebody who doesn't know something about titanium, but it's only a generation old. Like it's not much more than that. So to think that it's in every place, all of the engines that are flying us, across the globe, and that we've only understood how to deal with it for 50-ish years, 60 years is incredible to me, that we rely on it for such, monumental applications, that it's a testament to those who came before us and the hard work that they did to characterize it. So number 1, pretty young material for what we're using it for today. Number 2, the biocompatibility portion is always fascinating to me. You're going to be hard pressed to find something that somebody is, willing to put in their body more readily as a surgical implant than titanium would be. And that's a huge testament, again, to the amount of work that went into making sure that it was okay. Because I personally don't want to be the first guinea pig for a lot of medical things, but I did sign up to be the coronavirus vaccine because I'll take one for humanity on that front. But when it comes to a full implant, I'm not sure I want to be the first person. So I think it's just awesome that there were people in studies out there, and probably a lot of poor rabbits, that took the bullet for us when it comes to the manufacture of medical devices. And the third bit, it's not a material that anybody needs to be in awe of. It has its applications in all sorts of parts of the world, and there's a number of different ways that you could interact with it on a daily basis, whether that's a golf club, a watch strap, or your toilet paper. There's always a way you can look around and say, yeah, there's definitely more than I realized got me here. And then a big portion of that has the opportunity to be titanium.
Do you want to plug GE Additive real quick?
I love working for GE Additive. It's a huge benefit to my everyday life. I go to work happy every day that I get to do something new and cool. It is way, way, way beyond rapid prototyping now. There was the TMS conference in San Antonio that I went to, and I can't tell you the number of people that came by our booth because we were having an exhibit there. They're like, oh, rapid prototyping. And I said, oh, no. Did you fly here on a narrow body airplane? And they're like, yeah. I said, well, you could have had an additive part in that engine. There were also maybe additive parts in the structure of that aircraft. So it's way, way, way beyond rapid prototyping at this point. So if there's customers out there that still think it's just a one-off for a rig test, you'll never do it again, those people are missing a huge opportunity to revolutionize their parts and revolutionize their design. And the mechanical engineers and the people that understand qualification, and certainly the material scientists that exist inside of the additive ecosystem, are there, and they exist purely to help external customers accelerate the use of additive. So it's something that I get excited to do every day, is go in and work with these people and teach them, because that's at my core. What I like to do is, like I said, watch the light bulb go off.
Yep.
And every time I get to make that happen inside of the additive community, I feel, a little sense of pride as what the team that I was on, what we accomplished. It takes a village to get your first additive part, but then it snowballs. That's what I want to see, and that's what I think GE Additive is good at, is helping, build that snowball, and then we're going to, as a team, shove it down the hill and just watch it grow.
And so if you want to help our listeners, turn that light bulb on, how can they reach you?
So they can definitely contact me, and certainly my email address is just my first name dot my last name at ge.com. So daniel.frydryk@ge.com. A more formal approach, if you go to ge.com/additive, can use the contact us link or button or whatever it is these days, and just fill out a form. That goes to almost straight to an engineer. I won't say it doesn't get filtered by somebody, but that person's job is to make sure it goes to the right person. So if there's a question about availability of titanium alloy X, or how difficult it would be to develop titanium alloy Y, it would be in my inbox within a couple of hours of it being submitted. So like I said, we are in the business of making customers successful. So if people want to know more, we're going to take every opportunity to educate those people.
I think that's a great place to wrap it up. So thank you so much for joining us today, Dan. This was a blast. I definitely learned a lot about titanium and a lot of things I didn't know about it previously. So thank you for your insight on this.
It was my pleasure. It was a lot of fun.
Thank you for tuning in to this episode of the It's a Material World podcast. We look forward to releasing our next episode in 2 weeks. But until then, if you want to hear from us, we're on LinkedIn, Twitter, YouTube, and Instagram. Search for us as It's a Material World podcast. Links to our social media sites will also be in the show notes. If you have any feedback, we'd love to hear it. We're just two college students looking to get started with a podcast, and we want to grow the show with our community's input. You can send us feedback through messaging on any of our social media sites. Feel free to also provide feedback by messaging us directly on LinkedIn, either to Puneeth Upadhyaya or Thomas Miller. But until then, take care and stay healthy.